Hi everybody, this is the week 6 after party video for Math 137. We're going to go through some of the worksheet problems that we weren't able to get through in class, as well as a few extra examples to get some practice using the addition and subtraction formulas from section 7.3 and the various double and half angle formulas from section 7.4. Let's go ahead and start with one of our worksheet examples. This is number 9 from the 7.3 worksheets. We want to find solutions in the interval 0 to 2 pi for the given equation. Cosine of 3t times cosine of t minus sine of 3t sine of t is equal to minus 1/2. Now you might notice there that our left-hand side looks very similar to an angle addition formula for cosine. Cosine of u plus v is cosine u cosine v minus sine u sine v. And so we can, with 3t playing the role of u and t playing the role of v, we can rewrite the left-hand side. Is this the right size pen? Yeah. We can rewrite the left-hand side as cosine of 3t plus t. So we have cosine of 3t plus t is equal to 1/2. That's the same as cosine of 4t. And now we have ourselves a problem from section 7.2. Cosine of 4t is negative 1/2. There's going to be two branches here. Either 4t is equal to, let's see, cosine is negative 1/2 in the second quadrant at 2 pi over 3, I believe. And then we also want to do the plus 2 pi n here. Now we are ultimately going to just find the solutions in 0 to 2 pi. The other branch of this, 4t, would be, I'm just going to go negative 2 pi over 3 plus 2 pi n. That gets me the solution in the third quadrant. That's the nice thing about cosine. You can always find your second branch by doing minus the first branch. So make sure that looks like 4t. All right, and then in both these equations, we'll divide on both sides by 4. Here we'll get t is, pi over 6 plus, when I divide my 2 pi n by 4, I get pi over 2 times n. Here, when I divide on both sides by 2, we get negative pi over 6 plus pi over 2 times n. So if they wanted all the solutions, that would be our answer there. They just want the solutions in 0 to 2 pi. So this is where we're going to have to plug in different values of n and see what happens. Now, I think in class I made a chart to get that done. You don't necessarily need to do that. We can just say, all right, well, no, I guess it just makes it's too easy. It's too easy to organize your work when you do that. All right, so we'll call this pi over 6 plus 3 pi over 6 n, just so that I can have something with the same denominator, and minus pi over 6 plus 3 pi over 6 n. All right, now, just for the sake of it, when n is minus 1, I get pi over 6 minus 3 pi over 6 gives me negative 2 pi over 6, which is less than 0. So we don't want to keep that one. And here, we're not going to even compute it. When n is 0, I get pi over 6, which is between 0 and 2 pi. So we'll go ahead and keep that. Here, I get minus pi over 6, which is negative. So we're not going to keep that one. When n is equal to 1, here I get 4 pi over 6. When I add pi over 6 plus 3 pi over 6, that's the same as 2 pi over 3. That's between 0 and 2 pi. Over here I get 2 pi over 6, which is pi over 3, which is good. When n is 2, I get pi over 6 plus 6 pi over 6, which gives me 7 pi over 6. That is good. I guess our upper bound here would be 12 pi over 6 if we're looking for something in terms of denominator 6. So 7 pi over 6 is good. 7 pi is smaller than 12 pi. Here we'll get negative pi over 6 plus 6 pi over 6, which is 5 pi over 6. That is also good. When n is 3, we get pi over 6 plus 9 pi over 6, which is 10 pi over 6, which is 5 pi over 3. So that's good. So I guess in terms of pi over 3s, we are worried about 6 pi over 3. That's our upper bound in terms of over 3. Down here, or on the other side, negative pi over 6 plus 9 pi over 6 gives us 8 pi over 6, which is 4 pi over 3. So that's fine. And then when n is equal to 4, on this one we get pi over 6 plus 12 pi over 6. Actually, 12 pi over 6 is our upper bound. So this is definitely going to be too big. And over here, negative pi over 6 plus 12 pi over 6 gives 11 pi over 6. And that's going to be the last one. That's going to be the last one that we get down that. Notice that I get four solutions down each branch, and we were solving cosine of 4t is equal to negative 1/2. So we were expecting to have four times as many solutions down each branch. All right, now when I write these, it's always good form to write your answers or your solutions in order if you can. I think it's going to be pi over 3, 2 pi over 3, 5 pi over 6, 7 pi over 6, 4 pi over 3, 5 pi over 3, and 11 pi over 6. Oh, I forgot my pi over 6 at the beginning. Pi over 6. And 11 pi over 6, sorry. Is the last one. So those are my, do I get them all? I got them all. 8 solutions. All right. So that is the answer here. Now, I guess it was the very first step was using an angle addition formula, but the rest of this was straight up 7.2. Moving on to the next problem. I'm glad we didn't do that one in class. That one took a little bit longer than I had anticipated. We want to verify the identity. And this one's just going to be straightforward using the addition and subtraction formulas for sine. All right, so let's write down, we're going to start with our left-hand side and work to the right. Sine of u plus v plus sine of u minus v. The angle addition formula for sine says that sine of u plus v will be sine of u cosine of v plus cosine u sine v. That's my angle addition formula for sine. The angle subtraction formula for sine is very similar, except for it is sine of u cosine of v minus cosine u sine v. Now, since we're adding everything except for that very last thing which is subtracted, we can just erase these parentheses and notice that my cosine u sine v terms cancel out. I got a plus 1 there and a minus 1 there. And so we're left with 2 of these sine u's cosine v's. So that means I got 2 sine u cosine v. All right, that was short and sweet. Nothing too special there. Now these formulas, this formula is often used in reverse. If you have a product of sines and cosines, then, and you're not able, if you're trying to do something mathy, where you can't work with a product of sines and cosines, then you can turn it into a sum of sines using this formula. So for instance, if we had something that looked like 2 sine of 3x cosine of x, or let's just make it interesting, cosine of 7x. And supposing that whatever mathing that we're trying to do, we're not able to do it easily to this expression, we might think about using this formula in reverse and writing this as sine of 3x plus 7x plus sine of 3x minus 7x, and that would give us sine of 10x plus sine of minus 4x, which is sine of 10x minus sine of 4x using the formula for negative. Remember, sine of negative u is negative sine of u. That's one of our formulas for negatives. So anyways, sine of 10x. There are mathy things that you're going to want to do where, all right, we can deal with sine of 10x minus sine of 4x pretty easily compared to what we would need to do to deal with 2 sine of 3x cosine of 7x. I don't know how we would do this mathy thing. The thing I'm thinking of, which you would run into in a Calc 2 class, I'm not exactly sure how we would work, what the other strategy would be for working with it besides using this formula in reverse. Okay, a couple of bonus examples from 7.3. If you want to simplify this into a single expression, the idea here is the expression that we're given looks like the right-hand side of one of our addition or subtraction formulas. And in this case, it is the subtraction formula for tangent. So recall that tangent of u minus v is tangent u minus tangent v all over 1 plus tan u times tan v. All right, so here 132 degrees is playing the role of u, and 89 degrees is playing the role of v, and I guess ultimately we're going to want u minus v in this case. 132 minus 89 is, oh God, 43, I believe. Seems right. All right, I'm going to go with 43. All right, so I guess we can write this as, I mean, we could just copy that down. That's tan u minus tan v, and that's going to be tan u minus v, which is tangent of 43 degrees. So this problem is not, I wouldn't say it's terribly difficult if you're able to recognize the expression that you're given as one of your addition or subtraction or double or half angle formulas. All right, so it's going to be really important to just kind of know what each side of the equations look like. Last example, find the exact value of cosine of 255 degrees using special angles and addition subtraction formulas. We did one like this in class. The idea here is 255 degrees is not a special angle, but we might be able to recognize it as a sum or difference of special angles. So let's see, the special angles in terms of degrees would be 0 degrees, 30 degrees, 45, 60, 90, 120, 135, 150, 180, 210, 225, 240. We're getting up there. Let's see. Oh, we can write it as 225. Okay, I see. We could write it as, all right, 255 degrees is 225 plus 30. Okay, that's one way to go. Are there any other ways that we could get the job done? 210 plus 45. That's another way that we could have gone. That's not actually the way that I had expected to get the job done. We got 270 and 300. We could write this as 300 degrees minus 45. That's what I intended when I picked 255 degrees. I guess the point is there's going to be a lot of ways to get the job done. So anyways, let's go ahead and do this the way that I intended so that we can practice using the subtraction formula for cosine. That was kind of the point. Cosine of 255 degrees is cosine of 300 degrees minus 45 degrees. The subtraction formula for cosine, recall, cosine of u minus v is cosine u, cosine v minus sine u, sine v. So we have cosine of 300 degrees, cosine 45 degrees. Oh wait, sorry, this plus. It's plus. My bad. The subtraction formula for cosine gets a plus. Plus cosine of 300 degrees, cosine 45 degrees. All right, so let's, oops, those are supposed to be signs. I got distracted by my plus. Those are supposed to be signs. Man, I'm making all kinds of silly mistakes here. Sine and sine. All right, 45 degrees is easy. That's root 2 over 2, and that one's root 2 over 2. 300 degrees, that's down here, and the reference angle is 60 degrees. So it should have the same values with the right signs. So cosine of 300 degrees is the same as cosine of 60 degrees, which is 1/2. And sine of 300 degrees will be negative root 3 over 2. All right, so that'd be root 2 over 4 minus root 6 over 4, which is root 2 minus root 6 all over 4. I'm pretty sure we got that as an answer the other night. So a lot of these, we learned a lot of, we got comfortable with a lot of numbers, particular numbers, root 2 over 2, root 3 over 2, 1/2, root 3 over 3. We got comfortable with a lot of different numbers. We're going to see a lot of the same numbers pop up in these kinds of problems as well. All right, let's move on to some 7.4 problems that we skipped over. Verify the identity. Tangent 3u is tangent u times 3 minus tangent squared u all over 1 minus 3 tangent squared u. So this is kind of like a triple angle identity for tangent. And we will start off here using a similar trick. When we proved our double angle formulas in class, we wrote them as we did when we did like sine of 2u. We wrote that as sine of u plus u. So we're going to write 3u as 2u plus u. That's the trick here. And we have an angle addition formula for tangent. Let's write that down real quick. Tangent of u plus v is tangent u plus tangent v all over 1 minus tangent u times tangent v. So this will be tangent of 2u plus tangent of u all over 1 minus tangent of 2u times tangent of u. All right, kind of, this is playing the role of u and that's playing the role of v, even though I'm using the same letter. Hopefully it's not too confusing. All right, so there's our first step here, and then our second step would maybe use the double angle formula for tangent on both of these terms and see what happens. So let's go ahead and do that. Let's see our double angle formula for tangent. There's no point in writing it down twice. That would be 2 tangent u all over 1 minus tangent squared u. All right, so that's our formula for tangent of 2u, so it goes there on top, as well as, let's see, 2 tan u all over 1 minus tangent squared u, right here on the bottom. And then to clear out, I guess we got these nested fractions or compound fractions. We got these little fractions sitting inside the bigger fraction. And I think the easiest way to get rid of those in general is to just multiply on top and bottom by the least common denominator. Or any common denominator works, really, but you might have more work to do if you don't use a least common denominator. But the only denominator that shows up anywhere is this 1 minus tangent squared u. So we're going to multiply through on top. Don't forget to distribute. We're going to distribute that one onto both of those terms. And this one we're going to distribute onto both of those terms. All right. So on top, when I do the first distribution, I get just 2 tangent u. The denominator kind of cancels out when you multiply through, plus tangent u times 1 minus tangent squared u. So that's what we get when we distribute on top. On bottom, well, the 1 minus tangent squared u times 1 gives me 1 minus tangent squared u, minus, when we distribute on the second term here, we get some cancellation. We're just left with 2 tan u times tan u. All right, this denominator kind of gets canceled out. All right, then it looks like we have some simplification to do maybe. This will be, when I distribute the tangent u through on top here, I get 2 tan u plus tan u minus tangent cubed u. On bottom, this is obviously 2 tangent squared, and I got 1 minus a tangent squared minus another 2 tangent squared. So there's our 1 minus 3 tangent squared u that we're gunning for. All right, so our denominator is fixed up. And then I think we've got a couple more steps here. On top, I have 3 tangent u's. I got 2 tangent u plus another tangent u gives me 3 tangent u's minus a tangent cubed u. This should be a u here. It looks kind of like a 4. That should be a u. And I think, honestly, if we were going to try to come up with a good, oops, that's supposed to be squared. If we were trying to come up with a good triple angle formula for tangent, this looks pretty nice, but it looks like they went one more step and they factored out a tangent u on top. And our formula looks like this now. All right. All right, so that's what a triple angle formula might look like for tangent. Got a lot of practice there using our double angle formulas, and such. Now, in doing some grading of quizzes and things, I've noticed that some people are struggling with the algebra. Okay, once we applied our angle addition formula in this first step, and then we basically just wrote down our double angle formula for tangent in the second step. Everything that we did after that is, I would consider to be algebra. Now, I guess it's reasonable that, I think I've said it a couple times in class, I'm treating this whole chunk is just one kind of thing when I do this distribution on that step. All right? And so, like I said, I do consider that algebra, treating chunks of letters and symbols as expressions and just working with it. I would consider that to be algebra. So, yes, we are improving our algebra skills here, but I guess my point is, if you're making mistakes past that point, past this point, I would consider those to be algebra mistakes, as opposed to something related to new information. Now, I guess since we got a triple angle formula for tangent, we might as well get some triple angle formulas for sine and cosine just to see what those might look like. And the idea is going to be the same. So this is a bonus example. We're just going to see if we can find a nice triple angle formula for sine first. So we're going to write that as sine of 2u plus u. By the way, this is not something that, find formulas for these things is not something that you guys are going to be asked to do on any test. But it's just going to give us an opportunity to practice our angle addition formulas and our double angle formulas and doing some algebra with these trigonometric expressions. All right, so we're going to start off with the same trick that we started off with in the previous example, right? 3u is 2u plus u. And then use our angle addition formula for sine. That would be sine of 2u cosine of u plus cosine of 2u sine of u. Remember, maybe I'll use different letters here. Our angle addition formula, sine of alpha plus beta, will be sine of alpha cosine of beta plus cosine alpha sine of beta. So here, 2u is playing the role of alpha, and u is playing the role of beta. Now we have the opportunity to use a couple of double angle formulas. Sine of 2u is 2 sine u cosine u. I'm going to go ahead and get that going. So times cosine u. Cosine of 2u, we have three formulas for that. I'll just use the most, what I would consider to be kind of the foundation one, the one that's related to the angle addition formula for cosine. That would be cosine squared u minus sine squared u. Then we have some algebraic simplification that we can do. This first expression we can simplify to 2 sine u cosine, sine of u cosine squared u. That's cosine of u times cosine of u. Then I have a cosine squared u sine u when I distribute the sine u onto that term, minus sine cubed u. All right. Now this one, I don't think I like the way this one looks. I don't think I like the way that this looks. So let's see if we can get something that looks nicer. I guess, hey, we have an opportunity. I've got 2 cosine squared sitting here, right? Unless I've made a silly mistake. We got, oh no, wait, I take it back. I can combine those together. This is 3 sine u cosine squared u, because these are the same term. So I guess one thing that we could do is just factor out a sine and write this as sine of u times 3 cosine squared u minus sine squared u. So that's one thing that we could do. I guess that would kind of make it look very similar to the triple angle formula that we had for tangent. But here's what I was noticing before. I've got this cosine squared u. I can write everything in terms of sine, and having a triple angle formula for sine that is completely in terms of sine, I think that would be awesome. So let's go ahead and do that. 3 sine of u times 1 minus sine squared u minus, we still have this sine cubed u at the end. So we've got 3 sine u minus 3 sine cubed u minus another sine cubed u. So that ends up being 3 sine u minus 4 sine cubed u. I like that one the best. That's my favorite right there. All right, so we got a couple different candidates here for a triple angle formula for sine. Let's see if we can come up with something good for cosine. And by the way, guys, I'm just applying formulas and following my nose here. I have no idea how this is supposed to turn out. It's just an example I thought that we'd be able to practice doing some symbol pushing with our trig functions. We're just getting our hands dirty. We got our sandbox full of toys, and we're just pushing the sand around and seeing what kinds of fun castles and whatnot we can make. All right, we will start off the same way here with our cosine of 3u. Might as well push that up here from the start, because we're probably going to get to use most of our space. Let's see, our angle addition formula for cosine. Let's write this off on the side. Cosine of alpha plus beta will be cosine alpha. I didn't leave myself nearly enough space, I don't think, to get that written down. Cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. All right, so again, 2u is playing the role of alpha and u is playing the role of beta when we go to apply this here. So we have cosine of 2u cosine of u minus sine of 2u sine of u. And just like in the last problem, we can apply double angle formulas for the cosine term and the sine term. So let's go ahead and do that. I think I'm going to jump up here when I use the double angle formula for cosine. I'm going to use the one that looks like 2 cosine of u minus, 2 cosine squared u minus 1, because I think I want to head towards something that just involves cosines, if that's possible. All right, so remember we have 3, I guess we can write those off on the side here. We have 3 double angle formulas for cosine. The one that we used in the previous problem, cosine squared u minus sine squared u. The one that just involves cosines, 2 cosine squared u minus 1. And the one that just involves sines, 1 minus 2 sine squared u. And both of these you can get from the first one by using the Pythagorean identity in different ways. All right, so anyways, back to our problem. We need to use our double angle formula for sine, would be 2 sine of u cosine of u times sine of u. All right, so we have 2 cosine cubed u minus cosine u minus 2 sine squared u cosine u. So one path we could take would just be, all right, it looks like each of these terms has a cosine of u that I could pull out. Cosine of u times 2 cosine squared minus 1 minus 2 sine squared. And as soon as I see this 1, I immediately think maybe if I replace that with the Pythagorean thing, I might get something interesting. And I think we do. Let's do that. Cosine u times 2 cosine, it's supposed to be cosine squared u, minus cosine squared u plus sine squared u. I'm going to replace 1 with cosine squared u plus sine squared u. And then I have 2 cosine u minus, 2 cosine squared u minus cosine squared gives me just cosine squared u. And then I have a negative sine squared u minus 2 sine squared u gives me minus 3 sine squared u. All right, so there's one. There's one that kind of looks similar to this one up here, right? That's interesting. Look how close that these two formulas end up being. There's got to be something. See, now here's something where I would say there's something interesting going on. All right, our triple angle formulas end up looking very similar. Both of those forms do. So I think that that's interesting. All right, now if we had instead, let's see, I think up at this stage, instead of factoring out cosine u, if we had instead turned sines into cosines like we did in the previous problem, we get 2 cosine cubed u minus cosine u minus 2 times 1 minus cosine squared u. That's where we're using our Pythagorean identity. Sine squared u is 1 minus cosine squared u. And then we got a cosine u that's left here. All right, let's simplify that and see what we get. We have 2 cosine cubed u minus cosine u minus another 2. I got 2 times 1 times cosine u, or negative 2 times that times cosine u. So now minus another 2 cosine u's. And then I have plus, so a negative 2 times a negative cosine cubed u. So here we get 4 cosine cubed u minus 3 cosine u. And that formula looks very similar to this. Actually, I'm legitimately kind of surprised here. I'm legitimately surprised that these formulas end up being so very similar for the triple angle formula. So I'm glad we did that. There's some interesting stuff going on there. Apparently 3 is an interesting number. Because I guess here's why this is interesting. Here's why this is interesting. If I did sine of minus 3u, that would be minus sine of 3u, which is 4 sine cubed u minus 3 sine u. And so now that has the exact same form as that, just by throwing a minus sign on the inside. So there's something interesting going on there. And if I were slightly more interested in this stuff, I might try to figure out what's going on there. But I think it's time. We've played around in the sand enough here. let's go back to doing some more problems similar to the ones that you guys will likely run into on exams. All right, so we did a couple of examples at the end of class last night here. Simplify into a single expression. We have a couple more that we wanted to clear up, plus a bonus example. So in this first one, we need to recognize, let's see, we have one of our double angle formulas for tangent. Tangent of 2u is 2 tangent u times 1 minus tangent squared u. And that's exactly the form that this expression has, where 3 is playing the role of u. All right, so that will be tangent of 2 times 3, which is tangent of 6. See, there's not a whole lot. There's not a whole lot of work to do on these problems, because this is all thought bubble stuff. We're thinking, hey, this is the double angle formula for tangent, and 3 is playing the role of u in that formula. And then in the second one here, we have a half angle formula. This is what our book calls a half angle formula for sine. Sine of, I think our book uses v. I can't remember what letter I used in class the other night. Sine of v over 2 is plus or minus the square root of 1 minus cosine of v all over 2. That's one of the half angle formulas that we got. Now, like I said in class, this plus minus here doesn't mean that we have 2 answers. It just means that we have to pick. We have to pick the plus or minus depending on what v over 2 is. If we know that v over 2 is in the third quadrant, for instance, then we would pick the minus, or the third or fourth quadrant. So apparently, the minus has already been picked for us. So apparently whatever our v over 2 number is, it's going to end up being in the third or fourth quadrant. All right, now it looks like 414 degrees is playing the role of v. So v over 2 will be 207 degrees. So yeah, that is in the third quadrant. All right, so now all that's left is, all right, this is going to be sine of 207 degrees. There's not a whole lot of work to do. Like I said, this is all thought bubble stuff. If you wanted to show that work, your thought process, that would be a good idea to write this down, just in case you're wrong, so that you can show me what you know. But if you just write down sine of 207 degrees, I mean, that's legitimately the right kind of work. That's what's expected, I guess. All right, this last one. 1 plus cosine of 51 degrees all over 2. We do have a formula that kind of looks like that. We have a half angle identity or reduction of power formula that looks like cosine squared x is equal to, I think I wrote it as 1/2 times 1 plus cosine of 2x. Or you can write that as 1 plus cosine of 2x over 2. And that's the form. This is the form that our expression has. So it looks like 51 degrees is playing the role of 2x. And so x will end up being 51 degrees divided by 2, which is 25.5 degrees. So this will end up being cosine squared of 25.5 degrees. So like I said earlier, we want to be able to recognize when we're looking at a right-hand side of one of our angle addition or double angle or half angle identities or formulas. One more bonus example from 7.4. Given some information here about cosine of alpha. Cosine of alpha is negative 12 over 37, and also some information about alpha. So we can deal with this first one right away. Tangent of 2 alpha, we'll use a double angle formula to write this as 2 tangent alpha divided by 1 minus tangent squared alpha. That's our double angle formula for tangent. And so we got to determine what tangent is. Let's see, since alpha, we have 540 degrees is less than alpha is less than 630 degrees. So thinking about our unit circle here, we go around once, there's 360 degrees, and then there is 450 degrees, there's 540, and then there's 630 degrees. All right, so we're in quadrant 3. So tangent of alpha is going to be positive in quadrant 3. So, all right, let's go ahead and use our triangle now to figure out what the value of tangent of alpha is going to be. I wish there was a better word than absolute value for just like the absolute value. I wish there was a better, I don't like using the absolute value. I don't like using that terminology. But let's figure out what the absolute value of tangent alpha is. In this case, it is going to be what tangent of alpha is. We know that cosine is 12 over 37, so we can write 12 and a 37. And then using a Pythagorean theorem, our opposite side would be the square root of 37 squared minus 12 squared. So there's some calculator work. Where's my calculator? Got to get my calculator out and flip on some lights. All right, 37 squared minus 12 squared. That's 1,200. That's 1,225, and I'm guessing that's a nice perfect square. So let's take the square root of that and see what we get. Yeah, that's 35. All right, so my opposite side is 35. Tangent of alpha, just go ahead and do that over here. Opposite over adjacent would be 35 over 12. Actually, let's go ahead and write that over here. Tangent of alpha is 35 over 12 from our triangle, and using the fact that we're supposed to be positive, it just stays 35 over 12. All right, so we got 2 times 35 over 12 all over 1 minus 35 over 12 squared. And I think I want to multiply on top and bottom by 12 squared just to get rid of this denominator here. And when we do that, we get 24 times 35 all over 12 squared minus 35 squared. Okay, let's just try to do some arithmetic without busting out our calculators. Okay? Practice doing that. 12 squared minus 35 squared. I can factor that as a difference of squares. That's 12 plus 35 times 12 minus 35, which is 47 times negative 23. So 24, come on. Now in this case, I don't think it helps us any. 24 times 35 all over negative 23 times 47. Because, oh no, I think, no, this is fine. Nothing on the bottom factors, so we're not going to be able to do any nice cancellation. But I'll go ahead and write this as negative 24 times 35 all over 23 times 47. And I'm going to go ahead and be done with that. If we don't have a calculator at our disposal, there's not a whole lot we can do. I guess I used a calculator over here to get this. So I might as well use a calculator to finish that off. But we'll go ahead and save the calculator work for a different time. I didn't leave myself a whole lot of room to do the next one, so I'm just going to copy these down. Sine alpha minus beta and cosine of beta over 2. Cosine of beta over 2 is the one we're going to tackle next. All right, now we have a half-angle formula for beta. That'll be plus or minus the square root of, cosine, half-angle formula for cosine. 1 plus cosine of beta over 2. All right, and we can go look in beta. Let's see, beta, they tell us that we're going to do something slightly different here. Oh, I guess, no, we're fine. Beta is between negative 180 degrees and 90 degrees. So if I divide everything by 2, I get that beta over 2 is between negative 90 degrees, sorry, this would be negative, and negative 45 degrees. So that's somewhere in this range. But more importantly, we're in the fourth quadrant. So cosine of beta over 2 is going to be positive. All right, so we can get rid of that. We know that we're just going to do the square root of that. Do we have information about cosine of beta? No. We have tangent of beta. So let's get our triangle here. I'm just all over the place. I can't figure out where I want to put my work. I'm going to put this triangle here because it seems like a good place. I'm not going to put anything else there. So we got beta. Tangent is opposite over hypotenuse, 28 over 45. And then the hypotenuse will be the square root of 28 squared plus 45 squared. All right, let's do that real quick. Square root of 28 squared plus 45 squared on the calculator gives us exactly 53. All right, so this will be the square root of 1 plus cosine of beta is 45 over 53. And then to reduce this expression, I'll just multiply on top and bottom by 53. 53 plus 45 divided by 2 times 53, which is the square root of 98 divided by 2 times 53, which is the square root of 49 over 53. And that's how I will leave my answer for that one. These kind of get messy, don't they? They get messy with the computations. The double angle formula right at the beginning is pretty straightforward, but then when it comes time to simplifying the expressions, that's where things get messy. Sine of alpha minus beta is my last problem here. Right, using our subtraction formula for sine of alpha minus beta, that'll be sine of alpha cosine beta minus cosine alpha sine beta. And we've already made both of our triangles, so we should be able to read both of these off. Let's see. Well, we got to be careful here. And I don't know that I wasn't careful in the last problem. Hold on just a second. Oh, sorry. I wasn't careful, but it didn't work out. Cosine of beta over 2 was supposed to be positive, but cosine of beta was supposed to be negative. Oh, man, I screwed up. Cosine of beta was supposed to be negative 45 over 53. Okay, so that's supposed to be a minus there. And that's supposed to be a minus there, minus 45, which makes this number 8. And makes this 4 over 53. All right. I'm glad I made that mistake so that you guys don't have to. Okay, we got to be diligent. We got to be diligent with our triangles. See? I think that's one of the reasons why students don't like these triangles, and rightly so, because it's easy to forget to take the negative sign into consideration. All right, so let's see. We need sine of alpha to finish this up. We need sine of alpha and sine of beta and cosine of alpha and cosine of beta we already know is negative 45 over 53. Sine of beta, again, beta is between negative 180 and 90 degrees. Going backwards, we're in the third quadrant. So sine of beta is going to be negative, and using our triangle here, negative 28 over 53. All right, thinking about alpha. Alpha, I erased it, but I think we decided that alpha was in quadrant 3. Yeah. Alpha's in there it is, right there. Alpha's in quadrant 3. So sine and cosine of alpha are both going to be negative. Didn't leave myself a whole lot of room here. Referring back to my alpha triangle, sine of alpha is going to be 35 over 37, or rather, negative 35 over 37. And cosine of alpha, referring back to my alpha triangle up here, would be 12 over 37, or rather, negative 12 over 37. So when I plug the values into the expression that we have here, we have sine of alpha, negative 35 over 37, times cosine of beta is negative 45 over 53, minus cosine of alpha is negative 12 over 37, sine of beta be negative 28 over 53. And there's some calculator work to finish this off, but we'll go ahead and let you do that calculator work on your own. All right, I think that is all the examples that I had here. Hopefully these were helpful in letting us practice our various formulas that we learned last time in class, as well as some of the other ideas that show up in the context of doing these problems. If you have any questions about any of these problems or any of your homework problems, please contact me on Ivy Learn or via email or using the Ask Your Teacher feature of WebAssign. Otherwise, I will see you all next time. Thanks for watching.